All right. And then the lecture. Share my screen. Okay. So let's start. So in the last two lectures, we talked about material extrusion. There's one special type of material extrusion process, which is the composite material extrusion, which is, I would say, represents a future of this process. And why it is unique, let's take a look at it. So basically, the composite material has been a very important material in many applications, especially the ones requires a high the tensile stress as well as a lightweight. There are different ways to make this kind of material. And as you can see here, we have the manually up. Basically, those tapes is utilized to attach those composite fibers onto the polymer matrix. So we use this term polymer matrix to represent the base material of a composite material. And similarly, there's a manual bag or autoclave. So basically, the material is again attached to the base material. There are some automated fiber placement, like the one shown here, the thermal automated fiber placement. And with more automation in this process, you could have the manufacturing of such a composite material a higher efficiency. Here shows you a thermal composite automated fiber placement. As you can see here, the robot is placing the fibers onto the substrate or the base material, base part. But that's really difficult for making a larger parts like the one shown here. I mean, this one, right? Can you imagine there is a giant robot to do such a placement? That's not possible. And also there's other limitations for this automated fiber placement. First of all, it only allows the placement of the fibers with limited turning radius, usually 20 to 100 centimeters. Also, it is only useful for a simple core skin geometry like the one shown here. That means it requires a core, right? Basically, you are wrapping the fibers onto the core. But how about those components with a more buckle shape like the one shown here, right? That's difficult to make using those kind of placement. Basically, the automated fiber placement is kind of wrapping the fibers onto some existing core, right? That indicates its limitation actually, right? So you cannot do parts, something like, where's my mouse? Yeah, okay, something like this. So that motivates actually the additive manufacturing based fiber placement. But before that, let's look at some of the early work, which is the additive manufacturing of the cores. So as you can see here, these are the cores used in the automated fiber placement. And basically you will need to wrap the fibers onto these cores, Yeah, just a roughly illustration like this, right? And there are different types of cores. First of all, we have the washout cores. Basically, from the name, you can tell that that is removable water soluble 3D printed cores. So the material can be dissolved in water. Basically, you just print it and wrap the fiber on it, and then you could wash it out. So that's the washout cores. And there's a brick. There are breakaway cores, and those cores could be manually removed after the wrapping of the fibers. And there are other cores like these structural cores. So basically, these structural cores has a very good mechanical property, strength and tensile stress, such that you can leave it inside the part. You don't need to remove it, and this kind of structural shape can be produced by the additive manufacturing, and we can go through some details in later slides. Any questions so far? No? Okay, good. Yeah, again, the structural geometries. And I would say the most popular one is the so-called engineered lattice structure. So as you can see here, this is a typical engineered lattice structure. Actually, it's the I-beam. And it is the alternative to the honeycomb cores. And basically, there are different strut cross-section geometries. And in this kind of structure, this kind of basic strut geometry will be repeated, and it repeats itself and form a structural shape. And here shows you some applications. Basically, you can embed these structures inside a geometry as the skin, and the interior structure together with the exterior skin will work together for a part. It has a long history for such kind of structure to be embedded in a given geometry. Also, there are different unit cell geometries. Again, these cells repeat themselves to form a larger structures. And as you can see here, all different kinds of geometry are here. It could be utilized in many different applications. And the mechanical property of such a lattice structure actually are governed by several factors, such as the geometry, right? Actually, it's the most important thing for those engineered lattice structures. So different cell geometry will give you different material property. Also, the diameter or shape. I mean, by principle, if you have a thicker diameter for the strut, it will have a better mechanical property. Another parameter is the angles, right? You can make changes, for example, like this I-beams, right? You can make change of these angles, and by changing these, that could be a difference in terms of the mechanical property, and so on and so forth, right? To create such kind of composite parts, actually the extrusion-based process could work here. So the idea is, well, there will be two different material involved in the process. One is the base material, which is the thermoplastic.
Professor.
Yeah.
Sorry, one question for the previous slide.
Yeah.
Or the previous, sorry, previous to this slide. How, yes, because in my knowledge, for example, this can works for process to biocompatible parts in bone reconstruction. So how can I find these default geometries, and how can use in a customized design? For example, I have the part of the mandible. How can or in what program or what how I can put all this part for maybe after this process I can make an analysis for finite elements to I had to know if the mandible, for example, can with the belong to the movements in the mandible, for example. That I need for my for my work, for example.
that's
Sorry.
that's a good question. Actually, I mean, actually there are several software which is available for you to explore those geometries. They have pretty much all these geometries built in their software. So one software is the N topology. Let me put it in the chat box. You can find it. And
because I work with PIC in my country, polyether ketone, but we don't have porous, I guess that is the word. So this is interesting because exist parts or small parts to replace in the middle of the mandible in cases for tumors that we can replace with this structure. So so it's interesting for me.
Yeah, definitely. I mean, I just type it in the chat box. You can search the software and take a look at it. I'm not sure whether it has a free license, but I mean, I think you can at least know its capability and decide whether you will go with it or not. But that is there are some built-in softwares there to do this work. Another one, let me think. There's another one. I don't remember the name, but I can send you individually about another software which also has such a or I can share with everybody. I just make a post about this kind of software. I mean, that's very useful actually, as you mentioned, in those medical applications, as well as some lightweight structure, because you are reducing the material consumption, right? But at the same time, you have almost as good as a mechanical property with those solid parts. So it is in the, I would say, emerging, I mean, a frontier for this kind of research, and additive is the perfect process to produce it.
Thank you.
Okay, yeah, good question. Let's move on. Again, the idea is you have two different types of material. One is the thermoplastic, which will be built as the base material, and then you embed either the chopped fiber or the continuous fiber into the base material, as you can see in this illustration, right? Basically, one material, those fibers are embedded into the base material. So you have different options for the fibers, like carbon fibers, glass fibers, or Kevlar fibers, right? And as I mentioned, there could be either chopped fiber or the continuous fiber. In terms of I would say it's compare the two different options. If the chopped fiber is utilized, the process will be much easier. Why? Because basically you can do the extrusion of the fiber together with the base material. And in that case, the alignment of the embedded fiber will be essential. And actually, the embedded fiber flows through the nozzle, and the movement of the nozzle will guide the embedment of the fiber. So, and it turns out, if you look at this figure, it's a spiral shape, right? And if you zoom in and see, I mean, just imagine you can see through, right? And you will see all these fibers are aligned with how the nozzle move to create the shape. But if we look at this illustration again, it shows you how it is embedded. So then another question is how you're gonna distribute the fiber, and also how you're gonna decide what is the direction for the fiber to be aligned. That is actually very important in terms of the mechanical property of the parts. But before that, there's another thing you want to be aware of. That is the critical fiber length. Why this is critical? Because it decides what is the length, what is the minimum length of the fiber, such that if the actual fiber length is less than this critical length, then the fiber will pull out of the matrix rather than breaking. Because you have actually mixed two different material together. You have the thermoplastic as the base, you have the fiber to be embedded in the base. How to make them attached, adhere together, especially during the load is applied there. So you need to compute a length and make sure the fiber length will be greater or at least equal to this length, such that when you apply the load, the fiber will not be pulled out from the base material. So that's the idea. All right. Then what decides this critical fiber length? First of all, the tensile stress of the fiber, which is the sigma F over here, and also the fiber diameter. Another one is the shear stress of the bond between the matrix and the fiber. So that means if you have a larger bond, a larger shear strength of the bond, then you could have a less length, fiber length. So that's how you decide this critical fiber length. So be aware of this this equation, and there could be questions regarding this part. All right. Any questions? Okay, let's move on. So another important thing is this orientation of the fibers, as I mentioned previously, right? So if you look at this one, let's say this is the tensile axis. That means the load will be applied along this axis. Right? Oh, that's not good. let me erase it. All right. And the fiber, actually, the fibers are parallel to this tensile axis. Then you will have this stiffness, the combined stiffness of the two materials stiffness, which is the elastic, I mean, the plastic, thermoplastics elastic models, and also the composite materials. No, I mean the fibers elastic models, and you need to weight them with the volume fractions. That means the ratio of the volume for both the thermoplastic material and the fiber material. So that's how you get the overall elastic modulus, which is related to the stiffness of the composite material, right? Let's look at another possibility, which is the fiber actually is perpendicular. Those fibers are perpendicular to the tensile axis, and it turns out you have such a overall elastic modulus. But what does it mean? Well, if you look at these two figures, sorry. So we evaluate the elastic modulus and also the tensile stress of the composite material. And we also put the angle, different angles of the fiber orientation versus the tensile stress direction. So 0 means, well, it follows the tensile direction, and 90 means it is parallel to that. And turns out you will figure out, well, if the fiber is parallel to the tensile stress, tensile load direction, it has the best stiffness, the largest stiffness. And if it is 90, which means it is the fiber orientation is perpendicular to the tensile load direction, you will have the lowest stiffness, which is intuitive to us, right? So that means you need to be very careful when you decide which will be the fiber orientation during the process. For example, if you have this turbine blade, right? And obviously you want the tensile load axis be like this. That means you want to have your fiber to be oriented in this way as well. And that gives you the suggestion how you're gonna move your nozzle, because you want to align the chopped fiber orientation with the tensile axis. So can you tell me what's the way to move your nozzle when you build it? What's the building direction? Any idea? Okay, yeah. So let's say you have the part like this, and you want to have the your fiber to be oriented along this axis as well. That means you want to move your nozzle in this way as well. So that means you can never build your part if let me redraw it. It looks a little messy. That means you cannot build your part layer by layer in this direction. What I'm drawing are layers, just the illustration of layers. That means you cannot build your part and make the layers oriented like this. And then what you want to do is you want to build your part and the layers are like this. So then it will be the case the chopped fibers are oriented along the tensile axis. Now you get it. Get it? Mm-hmm. Okay, good.
Professor, I just wanted to clarify.
Yeah.
So what you're saying is when the part is printed, it's laying down sideways instead of like vertically upwards, like the longer side is laying down on the bed as
Yeah,
along the z-axis.
exactly.
Okay.
Yeah, same, basically, yeah, just as you said, you don't, if you print the part this way, it's never possible to place the fiber and make it to be aligned with this axis, right? So the only thing, the only way you could do it is, let me use a different color. Let me change it. Let me see. Okay. I think green is good. You print it, the layers are like this, and then that will fulfill the requirement, and then you will have the best tensile strength of the part.
Gotcha. That makes
Yep.
sense.
Okay. Any other question regarding this? Okay, good. I mean, that's the thing you want to keep in mind if you have such a application. And basically, this could be realized using the BAM process, which is the big area additive manufacturing, and those chopped carbon fiber together with the plastic pellet are mixed together during the process, and put them together, you could build a big part with a good tensile strength. But it could be that it could be quite challenging if you have something like this, right? That, how can you tell what is the tensile axis, right? That's even that's I would say almost impossible. Then how you gonna generate a tool path such that you have the best tensile test? I mean tensile strength. And after all, what you can only do will be run a like software, those optimizations. I mean the analysis software to figure out what are the strength. I mean the stress distribution, right? So let's still start from something simple like this L shape, right? And you have load to this wall, as you can see here. You have all the loads here, and here shows the fixture. Basically, these are fixed, and then you could run a finite element analysis using those software, and after that, you can see all those stress concentration. That means those are could be the weak point if you do not do some reinforcement, if you do not put more material there, or if you do not put the structural material near those regions, it will become some weak point. Okay. So in our case, that means you could do some make some fibers, put some fibers along these orientation like this during the process, and somehow this will be reinforced to make sure it will not be broken if the load applied this way. So that's how you could decide the fiber orientation. But this is only a 2D case. I mean, which is still manageable. But for 3D one, I'm sorry. But for 3D one, that's not that easy. And also it will make the tool path planning even more challenging, because you could have arbitrary direction for those stress concentration regions. That means the direction for the fiber orientations. So there are some process which enables the continuous fiber reinforcement, like the one shown here, which this machine is the Markforged. Oh, by the way, you will use Markforged in the lab session as well, but using the chopped fiber. This shows a continuous fiber. So let me stop the sound. Okay. Basically, it has two extruders. One is a nylon matrix extruder. It prints the substrate. In this case, it's the material in white color. And another extruder will print the continuous carbon glass or Kevlar material, I mean continuous fibers. And there will be a cutter after the embedment of the fiber completed. The cutter will cut the fiber, right? And that's the way you could embed those continuous fibers during the printing process. But this is not perfect. It only allows very small turning radius. And the printing speed is very slow if we compare it with the automated tape layup. Because it has a small turning radius, that means it compared to the traditional auto tape layup, it don't have the Markforged process has very little advantages. And also, again, it only works for 2D, right? Basically, it embeds the fiber for each of the layers. So how about you have some fiber, you want to place your fiber along the z-axis, right? That will make this process has no possibility to achieve it. And Markforged make the process and their software closed to the users. That means you cannot really see how the G code will look like and make changes to the G code such that you could customize the tool path, customize the fiber placement. I think that the reason for them to do so is this process is not that robust if they allow you to make changes to the orientations of the fibers as well as the turning angles. So overall, it is still in the, I would say, the preliminary stage for this process. Any question? All right, let's move on again. A little noisy, right? So this is another process which is embedding the metal wires. Actually, it's in this case is the copper wires. It embeds the copper wires into the thermoplastic basis. So if you look at the part after this layer is completed, what you will see is a copper wires embedded there. It's a very preliminary, but the idea is similar to what the Markforged does. That is print some base material and embed the wires into this layer. And then there will be a cutter to, or you manually cut it and then do the second layer and so on and so forth, right? So there are some other process and also to address the challenge of such a process. The biggest one, I mean, the biggest challenge here is the interlayer adhesion. So that means the bonding of the interlayer is not that good, especially for the amorphous thermoplastics. So there are this company basically they came up with a solution that is they have the carbon nanotube embedded during the process, and then they have another step that is the microwave energy to be applied during the extrusion to kind of fuse the material with carbon nanotube together, such that the bonding between layers will be improved. I mean, according to their statement, this is how they work. All right. So the current frontier or the cutting edge technology is the non-planar decomposition. So, as we mentioned, for those complex geometry 3D shape, on those kind of layer by layer process cannot satisfy its need for first create the geometry, second to place the fibers or the chopped fibers or continuous fibers into the geometry. So then the idea would be, how about we go a non-planar process, which is something like this. Let's look at the challenge first. If you look at this figure, here are some lattice structures, pyramid, right? Pyramid structures. And just imagine if you use the conventional AM process to produce it. For each of these strut, actually you are creating the geometry like this, right? This is one layer and another layer and so on and so forth. It has a very poor interlayer adhesion because they're only part of the area will overlap for different layers. If the angle becomes, I would say more from this one to here, you can see the bonding is, I mean, the overlap will become even less, and consequently the adhesion between the layers will become poorer. And also, it is extremely slow because you are creating them one layer by one layer and after another layer, right? So more intuitive way to produce this. So how about you extrude along this direction? Let me create redraw it. So for example, if you want to create this this strut, so what you want to do is, how about we just create this bar along this direction for the extrusion, right? That will solve this problem, these two problems. It has a much better adhesion between for this bar because it is created as a whole, right? And also the speed will be much faster. So actually that is what people are looking at. So this company is called Branch Technology, and they are making those large size parts and like house or home constructions. And they use the robot to extrude these materials, these structures. As the robot has the multiple degree freedoms, so they will extrude those strut along its axis, and also it enables the fiber placement. I mean the orientations of the fiber placement not just in XY plane, but also in the space, in the, I mean, Z direction, or in any 3D direction, by just extrude along the axis of the lattice struts. Sorry. So they are able to create some geometry like this in a larger scale compared to the most of the 3D printing processes. Actually, there are some challenges for the process. The first one is the splumping. Means if you print one axis and then another, how you prevent it falls down during this process, right? And also, I mean, to prevent this splumping, probably you want to cool down what you just print before you could print another part to join them together, right? Then you want to do the cooling during the process. So that's another challenging. So the third one is the collision of the nozzle with the previous printed part. I will show you some of the figures to have you better understand how this could be possible for the collisions, right? So let's look at this illustration. So if you have an extruder like this and you want to print those struts, so first of all, you print a filament onto the platform, and then you extrude your part in this direction. And at the same time with this extrusion happens, a cold air is applied to cool down the part, to make it solidified. And it will keep on cooling this part to make it stronger while the extruder is printing another bar to form this geometry, right? And turns out you will have some lattice structure or the some pyramid structure created. So for the extrusion, definitely you don't want to have something like this. Basically, it fall down and cannot hold them together. Basically, that's the case like this. How this happened? Because this is a continuous print. Means it goes here and then go in the descending way, and sorry, and it turns out because of gravity, this structure falls down, and something like this. So instead, instead of created the part in one pass, there are two pass process. First, you create this half, and then move your nozzle to here, and then go the ascending again to form this part. And it turns out this is a more robust process, and you can see all these kind of structure were able to be created using this kind of two-pass process. Collisions, right? Why is this happen? Because after all, the extruder is not just a dot. It has a volume. It has its geometry. That means in this case, if you have an existing structure like this, which is created previously, and you want to move your nozzle in this direction, there could be a collision between the nozzle versus this part. So in this case actually is related to the angle of this bar. So let's imagine you have a less angle like this, smaller angle like this. Then there will, if still you move your nozzle along this way, right? There will be no collision at all. So that is because of the nozzle, the angle of the nozzle, or angle of the structure, right? Another thing is the diameter of the extruder. As you can see here, if you have a smaller extruder, let's see something like this, then there will be no collision in this case. For this one, since the structure has such a height and your nozzle is like this, when the motion happens along this axis, let's see the nozzle move from here to here, there will be a collision between the nozzle and this part. Sometimes it cannot be avoided because after all, the nozzle has its geometry and volume, right? That's what you need to keep it in mind, because usually we only we simplify the nozzle to a dot, but actually it's not a dot, right? Just to keep this in mind. I might stop here and we can have a break. Let's go back at 10 a.m. All right. All right, let's continue. Okay. So what this could be realized, as I mentioned, is do this kind of multi-pass process instead of continuous move your nozzle and create this geometry. As you can see here, this printer is creating a complete unicell, and it always go ascending instead of descending. And during the process, there's always a cool air applied to solidify the printed strut, right? I think that is this video is taken by Dennis Cormier's students, and this shows how this process is creating some lattice structures as well as a skin.
I'm curious if the cool air is provided automatically or manually.
I think in this case, it's not a automatic process, but definitely it's possible to provide it. I think now right now they make this automated, but when taking this video it is not. And it's not difficult to make it automated. Basically, what you want to do is create just attach this this part with your nozzle, right? And and in the control side, just decide once one nozzle, one bar is created, then let the cool air out on the parts. So that's how it could be automated. Yeah. Any other question? Okay, good. So as you can see here, the orientation of the fiber, if you look at this zoom in view, you can see it is perfectly aligned with how you move your nozzle, which is the direction of this axis of the bar, right? And that achieves our requirement. And if you compare the printing time for these examples, and as you can see here, this axis, axial lattice extrusion is much faster than the the conventional fused deposition modeling. For printing the two example, one is a 3x3x1 lattice, another one is a block 3x3x3 lattice block, right? That's how you should think of this kind of a new process compared to the fused deposition, the conventional ones, fused deposition modeling, when printing those engineered lattice structures. All right. I think we have completed the introduction of the material extrusion process. And let's talk about some of the computational aspects of the material extrusion, which actually is for many processes, these computational aspects are universal, regardless what kind of process we are looking at. So let's look at some of the basics. The first one is the 3D printing file format. So I think in your first two labs, you have played with the STL file, right? This is what you use for the slicing, and it is necessary to take a closer look at this file. So what it contains for a STL file is tons of polygon patches and more specifically triangles in STL file. And these triangles actually is a approximation of the original geometry. And the process to get these triangles, which is called the tessellation, right? And if you open an ASCII STL file, you will see some of the lines of text like this, right? You have the keyword solid, then to get the file name is follows these keywords. And then you have the next, the lower level, which is a facet. This facet normal is listed here. So then you will have the three vertices, the coordinates of the three vertices, which form this triangle facets. And afterwards, you have the keyword, end loop, and end facet, and that is a complete triangles on the model. And you just repeat this for each of the triangles on the model. And after all, you will have another keyword, which is end solid. In that case, you just complete a ASCII format of an STL file for a model, right? So there are different ways to have the STL file. Basically, you can export the model using from the Fusion 360 or SolidWorks. And always you need to select the refinement level, and that will control the shape approximation quality. If you have a higher refinement, that means there will be more triangles to represent the 3D model. And as a result, you have a finer accuracy, shape approximation accuracy. Similarly, you have from SolidWorks, you also have those options like the one showing here, right? That will control the how fine the model look like or how coarse the model is. So for a STL file, actually, as I mentioned, it will describe each of the triangles forms the whole geometry, and the vertices for each of the triangle facets, actually they are listed in a counterclockwise direction. The reason for having such a counterclockwise direction, because you can easily use the right-hand rule, use your basically the right-hand rule will give you the normal direction, and your right hand, your other finger will follows the sequence of the vertices, and then your thumb will point outward of the part volume, and that is the reason you have such a counterclockwise direction, and you have such a sequence of the vertices in this direction. It actually has the information of the normal, right? And also, if you look at this this case, each of the edge of the triangle, actually they are shared by exact two facets. So this edge and this edge, actually they are the same one, and there's a one triangle and another triangle, they share the same edge, right? So if you look at this case, for example, these two neighboring triangles has each of them has 3 vertices, and if the vertices for the two triangles are listed as V1, V2, V3, and another one is V1, V2, V4, and you will immediately realize, well, one of the two triangles actually has a different normal direction. How? Again, by the right hand rule, right? Use your right hand, and basically these two finger will follows with those vertices, the sequence of vertices, and this sum will give you the normal direction, right? So for example, let's look at this triangle, V1, V2, V3. V1, where is it? Okay, here. V1, V2, V3. And use right hand rule, your thumb will point inward of the screen, right? But for in this triangle, V1, V2, V4, and you will have a normal direction which is pointing outward from of the screen, right? So that means these two normals are in opposite direction, right? That's how it works. Any questions? Okay. So as I mentioned, this is how a ASCII STL file look like, and it's very simple and readable, right? But the thing is, it has a larger file size compared to the binary one. So to save some of the storage space, the binary STL file is utilized as well. So if we look at this one, actually these codes represents a part of the cube. Actually, it's not a complete cube, but part of cube, some of the facets on this cube, right? So as I mentioned, the STL file actually is just a approximation of the geometry. Why? Because it has all the triangles on the all the triangles stored in the STL file, which is just a linear approximation of the original surface. So if we look at this illustration figure, we're actually looking at a surface, but it's not possible to look at a surface on a slide. So we use the curve to kind of mimic the case of the surface. Just imagine this curve is your surface, and then these straight line segments are the triangles facets, right? And basically, we are actually using those triangles to approximate the original surface. And there will be definitely a shape approximation error. And this error for the 2D curve case, basically you just use this distance over this chord. And then you will have some understanding how much this line segment is away from the original curve. That's how you compute the shape approximation error for a line segment to the original curve. So similarly for the surface, what you will do is use to compute the, to compute this, the distance of the center of the triangle to the original surface. And then you will have this this error, and also you could compute this radius of curvature, and turns out use this distance over the radius of a curvature, and turns out you have the shape approximation error, which is a little complicated, but you don't need to know how to compute it, but just understand, well, you are actually looking at a one linear approximation of the original surface. If you are using STL file, there will be some error. You definitely want to keep that in mind, because sometimes the error is too large. There will be some problems if you just use the STL file to create the shape. If that's the case, you want to reduce the error, you probably want to increase the shape refinement when you export your STL file. That means there will be more triangular face to approximate the original surface, right? Always need to find a balance between the file complexity versus the shape approximation error. Any question regarding this?
Yeah, Professor,
Yeah.
I just wanted to clarify. This is because when you draw it in like a software such as SolidWorks or
Yeah.
whatnot, it draws it as a straight line, but when you print it, it prints it as a curve. Is that why
No,
there's this?
actually, it's the opposite way.
Okay.
When you draw the geometry, it's a surface, right? It's a parametric surface. That means there is a circle, there is a sphere, but when you export it to STL file, there's no real circle, there's no real sphere. You only use those planar triangles to approximate the original surface and original curve, such that when you print it, you actually print the approximated model, which is the linear approximation. So that is why there could be some errors.
And this is on like a really, really small scale, right? Because
Well, sometimes it's not that small. Again, according to how accurate you want your print is. I mean, in many cases, it doesn't matter, right? But in some cases, for example, some really precise like mechanical parts, you want to make sure the assemble of the two pieces will be accurate enough. That has the requirement for the shape approximation. It again, depending on your applications. Yeah.
okay, thank you.
Yeah. So just keep that in mind, right? That somehow will affect your decision making when you export your part from the CAD software, right? Another problem for the STL file is its redundancy. Why it is redundant? Just to look at this shape. As I mentioned, actually these pairs of edges are actually the same edge. Actually, it is something like this. Each of the facets share the same edge, but in STL file, they are separate. Means you, in this triangle, you have all the three vertices listed. And in this triangle, all the three vertices are listed. In this one, same. In this one, same. So actually, it has a duplication of the vertices like the one shown here. It doubles the vertices, and in this case, there are 4 times the redundancy. Same thing happens here. Similarly happens here. So you're actually storing more than it is need. If you have some way to share these informations, you don't actually need to repeat these for each of the facet. For example, if we look at a model with 63,000 facets, so the file size for different file format, if you look at the STL file, it takes 11 megabytes for the ASCII format and 3 megabytes for the binaries. And for all the other file format, it takes less file size compared to both binary STL and ASCII STL. So that is because the redundancy of the information STL file stores. And that's why there are more other alternatives than STL file to be adopted in many applications, right? As I mentioned, there's a round-off errors because of the shape approximation, right? And that is another problem for the STL file as well. If you want to find some information about the alternative file format to the STL file format, you can check this website to look for more information. Actually, for STL file, there's I will say a more serious problem is it only stores those triangles and no any other information, for example, the colors or material properties. But that's not desirable for many processes like the one shown here, these color printing process. It requires you specify the colors. And that's why these file format will be used for such a color printing process. The VRML, OBJ, and PLY file. All these file formats support the color information to be stored. And then we come to another topic, which is the transformation of the geometry. Basically, that is very important, especially for the slicing. You want to move or rotate the part to make it the best orientation for the slicing. And also sometimes you want to scale down or up the virtual file to have a different size of the printed objects. And there's other problems like the access convention. You want to use the right hand side. Right hand, right? The axis could be your thumb and your pointer finger Y and middle finger Z, and you will span a axis coordinate system, right? That is how you could use your bare hand to have such an understanding of the axis. But actually, these kind of translation, rotation, and scaling can be easily done using the matrix multiplication. And for the matrix multiplication, there are details you could find through those math, linear algebra lectures online, but you just want to keep the simplest understanding of it. That is, for this multiplication of matrix A times matrix B, the only thing it would happen is the columns number of matrix A must equal the row number of matrix B. For example, this one. This matrix has 2 row but 4 column, and this matrix has 4 row and 3 columns. And if we put it here, that's 2 by 4, right? And this has a 4 by 3. Well, you check the column 4, the row 4. Okay, it could be multiplied. And turns out this is the resultant matrix. So I think that's the only thing you want to understand. And of course, the rules for how you do the matrix multiplication. I don't want to repeat it here, but if you forgot it, you can go and review your linear algebra textbook. But in the transformation of the model, this is the key for implementing this process. So let's look at those transformation one by one. First one is the translation. That means you move a part by a distance along certain axis. For example, you could move your part along the axis by A, along the y-axis by B, and C along the along the z-axis by C. So all you want to do is you just put this translation of along each of the axes to these positions. This is the transformation matrix, right? Basically, this part, it will be used for the rotation. I just use R to represent. And these 3 values will be the translation. And this number is the scaling, right? And that's, overall, this is a transformation matrix. And this xm, ym, zm is the coordinates of one vertices. And this one, xw, yw, zw, is the result of, is the position of this vertices after you apply this transformation. The original one, original position, and the new position. And this is the transformation matrix. All right, so you got it? So all you want to do is to find out these transformation matrix and apply it to the original position of a vertices, or all the vertices on the model. And it turns out you will have the new positions, right? So for the rotation, you could rotate a vertex by any angle about all 3 axes. If we look at the one which is rotated about the axis, then you want to put these numbers to these positions. And basically that's the rotational matrix for a vertices or a part about the x-axis. And similarly, this is for the rotation about y-axis. And then we have the rotation about the z-axis. And the scaling, right? So basically, you have a scale factor in different direction, and you could easily put it along this sorry, along this diagonal, and each of the components of the factor gives you the scaling factor for x, y, and z direction, right? And that's a scaling matrix. Let's look at one example. If we have a point 0, 0, 1, and we want to translate it 5 units in the y direction, and then rotate this point by an angle of 90 degrees along the x-axis, what will be the new coordinate? So what you want to do is just follow the others and figure out what are the matrix associated with these operations. The first one is translation, right? 5 units. What you want to do is, well, this is for x, y, and z, and for x and z, nothing, but 5 units along y direction. Then put 5 here, and keep all the rest to be like this. All the diagonals are 1, and all the rest are 0. Use this translation times your points. What is your point? 0, 0, 1, 0, 0, 1, and leave the 1 here. This does not change, right? It turns out you will have your final matrix. The position after this translation, right? Which is 0, 5, 1, and then do the rotation. It is a rotation along the x-axis. Then plug in those numbers to the matrix at the right places, and then apply this rotational matrix to this translated position, which is the result of here. And turns out you will have the final position of your of this point, which is 0, negative 1, 5, right here. And that is how you translate and then rotate this point. So sometimes you can just have a concatenate, basically composited matrix. That is, you multiply each of the transformation matrix together and form a overall transformation matrix, which is called the concatenation matrix in this case. And you just follow the sequence of your the transformation. For example, in this case, so this translation matrix will be the rightmost, will be here, and then you have another rotation happens and put it right-hand side of your first transformation. Let's see if you have another rotation, scaling, or translation, just put it here, and you can keep on multiplying your matrix based on the sequence of this transformation. For example, in this the same question, right? You first do a translation and then do a rotation. Again, the first transformation matrix is placed the rightmost, and then the second transformation, if there are others, just to put it in this way, and by put them together, you will have an overall the concatenation transformation matrix like this, and use this as the overall transformation matrix, and multiply this with the position of the the position of a point, and turns out you will have the same result as what we have previously. All right. Any questions? Nope. Okay. So you will have some practice for having this for this part, right? There will be some questions related to this. So with all this explained, what is the process for the for preparing a 3D printing file? Usually you want to first 3D scan a part and then convert the part to the point cloud from the scanner into surfaces. And then you could repair the damages of the reconstructed surface, or there will be some flipped normals on the surface. You can repair it using some software and apply colors of the model and save the model together with the color information. Or you could even put some structure, lattice structure or some interior structures to make it a lightweight part. After doing all of these, you can export the result to certain file format. If you are talking about some color printing, basically you do not go with STL, go to VRML, OBJ, or PLY, or some other file format. And then use the output file, do the slicing together with the sliced file. You can do the 3D printing based on that. So that's the a typical procedure to prepare the 3D printing file. So there for the mesh repairing and also some other operation, you could use the MeshLab software, right? You can download it on this website. It's a freeware. Another freeware is the Autodesk Mesh Mixer. Basically, it provides a rich library of those mesh-based operations. So this is for mesh, not for the CAD files. Basically, you have to have a mesh file format first. OBJ, STL, or PLY, I think also works. But what you could do is you could repair it by filling holes, and also you could do some mesh editing, do some mesh sculptures or cut, mirroring, or do some mesh composition, meaning you have one part from one model and another part from another model, and you can mix the two together to form a single model, something like this. Very interesting software. But back to the mainstream, no matter how you prepare your file, I mean the geometry, there's a one last step is the slicing. So as you can see here, this 3D model is sliced to all these different layers. And also for each layer, there will be the tool path generated like the one shown here, this kind of infill structures. And all of these will be stored as a G code, which is available for our Pulsar machine, right? Sorry. So some factors for the slicing. The number one is layer thickness. For the original shape, this semi-sphere, you could have different layers, and accordingly, the surface roughness or surface shape approximation will be different. The one with more layers usually has a better surface roughness or smoothness. But how you do this slicing, right? Basically, you are using a plane to cut your model. So this plane, if you assume the printing is along z-axis, the plane actually is something like this. Z equals t, then z equals 2t, 3t, and so on and so forth. And t is the layer thickness. If you assume the model is placed on the platform and the printing is conducted along the axis, that's the equation for the slicing planes, right? So if we look at this, so what all you want to do is to do the plane triangle intersection. You want to figure out the intersection points of one cutting plane with all the triangles on the model. And the point where a slicing plane cuts through a facet edge actually is called the trigger point. For example, I think there's some illustration later to tell you how this intersection to be computed. So just imagine once a cutting plane is applied to the model, and there will be series of trigger points obtained. And this trigger point will be linked to a loop. It could be either the contour or the holes on the model. For example, like in this case, this for each of the for the slice, it has an outer boundary and also a inner holes. There are two loops, and basically for the outer loop, we store the points on the loop in the counterclockwise direction, and for the inner loop, we store the points in the clockwise direction. Why they are different? Actually, that is for the convenience of the nozzle motion. So if you define if you store the loop in this way, basically when the nozzle moves along these directions, the material, the side with material fill in will be always the left-hand side, right? If you look at this, let's see your nozzle move along this, then the left-hand side will be the side with material filled, right? So same thing happens if you move your nozzle along this loop. Again, left-hand side is where the material should be filled in. So that is the trick. That's why for the outer loop, the points are stored in counterclockwise, and in the inner loop, all the points are stored in the clockwise direction. Any question for this? All right, good. So how you decide which loop is the outer boundary loop or the inner holes, inner loops? Well, that is related to the evaluation for each of the loops, whether a loop is inside another loop. And turns out that is related to the inside out judgment or computation. And I will skip the details, but there are robust algorithms to decide whether a loop is totally inside another loop or not. If not, that means that is a outer loop. If yes, that means it is an inner loop, which is a hole in this case, right? So the sliced data, the information will be used for forming a toolpath. Let's take an even closer loop, a close look at the slicing computation. So just imagine you have such a cylinder shape like this, and how could you have a sliced layer? Actually, as I mentioned, basically you are computing these intersection points, which are the trigger points, right? And what you want to do is basically, let's see, these are the equations for one triangular edge. This is the equation for a triangular edge where x1 and x2 are, I mean, x1, x2, y1, y2, z1, z2. These are the coordinates of the two endpoints of the triangle edge. If we look at this figure, this is one endpoint of the triangle edge, and this is the second point of the triangle edge. And you want to find out this intersection point. And you've already know the this plane equation of the cutting plane, right? Which is z equal to something. The layer the overall thickness at this plane, right? So you want to combine the two equations together and substitute z into this equation, and then you will solve the x and y. So it turns out that is the x and y coordinates of the intersection point. Because z is known, that is the current slicing plane height, right? And the only thing you want to obtain are the x, y position. And that could be obtained using these two equations. So that's how you could have one intersection point in this case. Any questions so far? All right, good. So let's take a look at an example. That could be there could be some calculations in your homework as well as the quizzes. But let's look at this example first. For this triangle, you have one endpoint with this coordinates, and this one is another endpoint. And there's a cutting plane with z equal to 3 as the plane equation. And how you find the coordinate of this one? So just use the equation on this page and substitute all the values. Turns out this is the x position, y position, and the z position of this point. So that's how you compute this. Any question? All right, good. So once you have all the trigger point computed, you could actually have a series of linked points by finding the match. And turns out you could have a loop, which is a series of trigger points, one by one. And then two neighboring trigger points actually are in the same triangles. And that will be used for the following calculation. For example, you want to create the infill patterns for the contour. For the infill, if we find out the simplest one is the patch, or those so-called rectangular infill. So what you want to do is, sorry, for each of the layer, for each of the contour, use a series of straight lines, which are either parallel to x-axis or parallel to y-axis, and again compute the intersection. And then you will have all the intersection points, and it turns out you will have all the infill created. All right. So another point is the bounding point box. So bounding box actually gives you a minimum and a maximum X and Y, Z values on your part. So for example, if you look at this part, you will have such a bounding box created, which will be the minimum cuboid volume, which covers the whole model. And that is very useful as well. But first you want to align this bounding box to your X, Y, Z axis. Right? So another calculation is the support material. So for example, if you look at this T shape, any point which is pointing downward along the Z-axis needs to be supported. So in the STL file, if you have your slicing implement along the Z-axis, means you are printing along the Z-axis, then check each of the surface normal vector. If the Z components of that vector, the normal vector, is negative, that means that facet is pointing downward, which means you need to print support material. That's the simplest way to determine which facets need to be supported. So keep this in mind. There could be questions asking you, well, there's a surface normal like this on that facet. Tell me whether this facet requires support or not. So you should be easily come up with the answer by looking at the Z components of the normal vector, right? Sorry. And here is a simple algorithm to determine whether the support is needed for each of the layer. And actually it is started from the topmost layer and go all the way top through go the top down sequence from the topmost layer to the bottommost layers. And I don't want to go to details. You can take a look at this, but that's very interesting algorithm. And it works very well, although it could generate more than enough support, but that's the most secured way to support your part. So sometimes you just want to compute the area of the slice to estimate the material requires for a layer. And this equation gives you how you compute the area. And this area you want to be aware of. This area has a sign. That means there could be a positive area or negative area. The sign will be positive if the given loop is a counterclockwise loop, means the exterior loop, that's a boundary loop. And it could be negative for the counterclockwise, for the clockwise loops, that means interior holes. So if you put all the wall surface together, the area together, basically you are subtracting those negative area, and it turns out you will have the actual area for that layer. So if you look at this, for example, you have one layer like this, you have one loop like this, and another loop like this, and this is the hole, right? This is the hole. So to compute the area, you are using the area of, erase. You are actually using this area minus this area, right? Always forgot to use a different color, but you got it, right? And it turns out you will have the area of these regions, right? Right. So that's how you could have a estimation of the area of each layers. Any question for this? Okay, good. Again, another example, if a sequence of vertices are given like this, and here those arrow shows its order, right? And follow using this order and substitute the numbers into this equation, you will come up with a area which is a negative value. Again, that means that it is a hole, an interior loop. So the building volume, I mean, the consumed material could be estimated using the area of each layer. Basically, you sum up the area of all slice. Then you have a total slice area. And with the area and the layer thickness, you can have the overall build volumes, right? But that's not the only volume to be consumed. There will be the support material volumes if there are support material. So you want to also need to estimate that volume as well. So that's how you build up the estimate the build up volume, and that's how you build up estimate the material cost if you have such a volume, right? Another estimation is the build time, but that's not a easy task. It is a process specific. For that is because different material process has different time for each of the layer. Also, after building each of the layer, there could be some different time in between of each of the layer. Also, there could be some post-processing time for different processes. So it's highly related to what kind of process you are looking at, right? The last one is the nesting. That is for a given build volume of a printer and a given set of model to be printed, how are you going to pack the model such that you could fully utilize the printing volume? So some results are like this. Where's my mouse? Yeah, here. Right. This is the result of a good packing. You are optimizing the building volume of this printer. And there are some software could provide such a layout, such a packing layout for you to print multiple parts in a same run of printing. Well, that's pretty much all we have for today's lecture. There will be another homework associated with these two lectures. I think specifically the calculation part, computation part. Another thing will be the exam 1. So I'm planning to have the exam 1 the week after next week. That means, what's the date? 27th, Monday 27th, same time of the lecture. I will post the questions to my courses. You just download it, complete complete your answers to the questions and take picture or scan it, I don't care, and then upload it to my courses, just like what you do for your homeworks. And it will cover all the content within about I mean all the content including the computation from the lecture 1 to here. So that's all the exam will cover. And also the questions will be similar to the homework questions. So be aware of the homeworks. Oh, by the way, I will release the homework 1 solution as well as your scores by tomorrow. All right. So any questions?
Yeah, good morning. I have one question. Can you just review the format of the exam? You said we're gonna have to download it on my courses and re-upload it there too?
Yeah,
Like when we finish the solutions?
just like what you did for your homework 1. Same thing. Yep. Any other question?
Did you say there's a homework 2 this week or no?
Yes, I will release it after this lecture.
Okay, thanks.
Yep. Yep. Anything else? No? Okay, I think that's all for today's lecture. And thanks for your attention. See you next week.
Thank you. Have a good day.
Yeah, you too.
Thanks, Professor.
Yep.
Thank you.
Yep. See you guys.